Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process by Sir Jagdish Chandra Bose, who was a very legendary scientist during independence era. He says, the poet is intimate with truth, while the scientist approaches it awkwardly. Come some day to my laboratory and see the equivocal testimony of the crescograph, which he had designed to find out that the trees are having the life and they can sense it. And that is why he was talking like how the poet is intimate with the truth and scientist approaches it accordingly. Let us recall what we learned in the last lecture. In the last lecture, we initiated discussion on hybrid propellant rocket engine and we looked at historical evolution. Then we moved into the various components of the hybrid propellant rocket engine and then fuel grain configurations, and then we looked at very briefly about the complex processes involved during the combustion of the solid the hybrid propellant combustion. And in the process we derived a semi-empirical relationship for regression rate, and we will be discussing little bit more about that. Let us consider that this is your cylindrical grain and in which you are having a propellant, and this is your side views which you are showing here, and let us say this is your propellant through which this is your fuel grain and this is your oxidizer which will passing through that, and this is basically rho oxidizer, V oxidizer. And keep in mind that we derived this thing and this we call it as a G oxidizer. But if you look at G total oxidizer, total G is basically G of oxidizer. Beside this fuel which will be regressing from here due to the burning of the fuel grain, and this will be also coming to that, and that I can call it as a GFFX. That means this G is changing along with the length, and if I consider this is your length of the fuel grain, it is changing along with that, and this G F I can calculate that by considering this is 4 rho F and 0 to x and R x by d h, and this is your hydraulic diameter, and if I integrate I can get that thing, that is d h is equal to basically 4 a by p, and keep in mind that d h is your hydraulic diameter. And this p is your perimeter, this p is your perimeter, and this is your cross sectional area, right, cross sectional area. That means it is changing, and let us look at the how does the regression rate vary in a circular port, and this is your circular port, and this is your fuel grain. And as I discussed in the last lecture, the expression for the regression rate is equal to rho f r dot is equal to 0.038 g power to the n and x by mu g m b power to 0. Keep in mind that I had now exchanged that, earlier it was m here and this n, but it is basically coefficient which will be different. And if I consider this n is 0.75 in this case and m is minus 0.15 and oxygen mass flow rate is 7.95 kg per second, density of the fuel is 1000 kg per meter cube, and I am considering the blowing ratio is 1. Okay. So, if I will look at how this regression rate is changing, with that you can see that is basically regression rate is plotted along with x, and to start to it, of course, it will be having 0.1 second, which is having a very larger regression rate at the front end of this grain, and then after that it decreases. And of course, as the time increases to 20 second, this is again lowered down, but is having similar features. So, this is basically region or this region where the boundary layer effect will be more, because the boundary layer in this case will be small. This is your boundary layer, and therefore, the heat transfer to the fuel grain will be higher, and so that you are getting higher regression rate. But as it goes on, it is remaining almost constant. So, you can say that the hybrid propellant provides almost a constant regression rate at the downstream of the fuel port, because from the x, and this is starting from your at the x direction, you can say. And the another interesting feature, you can say that x, this is your m, is represent a boundary layer growth, and that causes a decrease in heat flux, which is balanced by the total mass flux due to fuel addition. Because of this fuel addition, there will be increase in the g, but however, the area of the cross section also is increasing. So, that has to be balanced, so that you will get a steady combustion, otherwise it will be in trouble. So, a higher cross section leads to a reduction in the local mass flux, tending to the level of regression rate, because the total mass flux will be changing, because area is changing much faster rate as compared to the mass flux which is passing into the port due to the burning of the solid fuel, and hence it displays a self regulating features and less likely to cause explosion due to sudden fissure in the fuel grain during its operation. If you recall that we had learned earlier that if there is a fissure here, let us say if there is a fissure over here, right, due to crack, let us say crack or a fissure kind of thing, then what will happen? Surface area will increase, and if the surface area will increase, then naturally the regression rate will be, the amount of mass flux which will be generated will be higher, and then the pressure may go up. But here what is happening, because of area is increasing, therefore, the flux will be reduced locally, and then you may not get that effect. That is the beauty of the hybrid propellant rocket engine, as it is less prone to the explosion as compared to the solid propellant combustion engine, due to the sudden fissure or the crack on the solid fuel grain. So, let us look at discuss about little bit about regression rate. We know that regression rate of the solid fuel grain depends on the type of fuel, its metal loading and fuel port size, atomizer design, and also the flow structure, because the flow will be turbulent, and also it will be sometimes creating some kind of a vortices also, and fluid property variation boundary layer, because temperature will be changing. So, also mass flow rate and then other things. So, therefore, the property of the fluid will be also changing. So, that means it is quite complex as compared to your solid propellant combustion engine or the liquid propellant. So, let us look at qualitatively the regression rate, which is plotted in the log scale along the vertical direction, and the mass flux along the horizontal direction. Generally, we will get a relationship which is power to G 0.8 that we had seen earlier, and due to the geometry or the scale or the additives, there will be increase in both the direction, but this is due to the diffusion flame combustion or the diffusion combustion. This is basically I can say that diffusion controlled combustion. In other words, that regression rate will be dependent on the diffusion, and also there will be turbulent heat transfer as I told. But if I extrapolate this thing to here with the decrease in the mass flux, what I expect this will be like this. However, this mass flux is lower, therefore, the convection will be lower. In this case, the radiation, thermal radiation effect will be higher, and there might be of course, the metal loading. If the percentage of metal may also increase, then the convection is lower, and there is a pressure which will be affecting the radiation pressure into diameter that control the regression rate. And then with increase in the pressure or the into diameter, that is one case, or increase in the metal additives, then what will happen, the regression rate will be increasing, because of fact that there will be optical radiations will be higher in with the increase in this, therefore, the regression rate will be higher. Like if you look at this will be higher. But when the mass flux is reduced further, then what will happen, there will be melting of the surfaces will be there, and then a char is being formed, and there will be subsurface decomposition that can occur due to penetration of the thermal wave leading to unstable combustions. And this is threshold is known as the cooking limit, because beyond that you can go up. This is known as cooking or the melting limit. And this can cause the chafing instability. You might be knowing chafing is a low frequency pressure oscillations, which may be caused by the perpetual repeating mechanical removal of the soft layer, because already the there is a char is being formed, and this become very subjected to variation in the char the surfaces, because all these are being melted out. So, therefore, there will be pressure oscillation, hence it must not be operated in this range. And let us look at the other extreme case, where there will be very high mass flux region, this in this region, where the chemical kinetics will be playing a role, and there will be, if you look at Arrhenius equations, that if the pressure is will be increasing, then of course, the flame surface will be coming near that, and then it may be a little premix flame mode kind of things, and then with increase in pressure, reaction rate will be little decrease. So, and then the regression affected and the PC, at certain PC the regression rate decreases as compared to the predicted value. This is the lower values will be coming, and with further increase in G, there will be flooding limit beyond that, which is not shown in this region. This which can occur for the reactive of fuel and oxidizer system, particularly when the lithium hydride or the fluorine is being used, and this has to be, flooding effect has to be avoided in case of hybrid propellant rocket engine. So, if you look at the range in which it can operate well, is basically this turbulent heat transfer region, but you can go little further by with the decrease in the mass flux ratio or the increase in, but you should not go beyond certain limit of the cooking limit, or the flooding limit has to be avoided for its operation. So, this is the important thing that you should keep in mind. And let us look at types of port configuration one can think of for hybrid propellant rocket engine, and of course, the several design one can think of, but I will be discussing about only few of them. This is your cylindrical fuel grain, which is having limitation, as I told, that it cannot be really used for a larger rocket engine with a high combustion efficiency and higher thrust. Therefore, the multi-port people use, and if you look at that, this is the double D, which is having 2 ports, then it will be also difficult to design, because this surface will be moving in this direction. So, if you look at regression rate will be going, and then this also will be curved one, and then the if and this also again will be curved, and then maybe regressing. That now one has to design properly, and it is having limitation similar to cylindrical port fuel grain, and it can be used for a little higher thrust level as compared to cylindrical, but however, it is having own limitations. And there is another one which is having 7 cylinder clusters. Of course, people can go for different one. These are the each one is cylindrical one, and that has been compact into another casing. This is known as casing, and total is 7 of them people have used. This is a very good one as compared to cylindrical, and we will see. And besides this, the 4 port wagon wheels, and the wagon wheel is the most popular one among all these things, and which is being used. If you look at this, a 4 port, and this is having curved surface, and to design this is not that easy, but however, if you increase the number of ports to more, it became triangular shape, and that you can see here. And this is also being used, but it is having limitation also. The structural rigidity will be very low, or the strength will be low as compared to the 4 port wagon wheel and others. And there is a double rows where this will be more having that, and it is a little complex to design as compared to the wagon wheel. And let us look at this, as I told earlier, this port will be having a fuel support wave, which will be basically having certain propellant, but it is regression rate much lower as compared to that. So, that it will be giving a structural support to this port, not being broken down due to the low strength when it is regressing. So, it is having of course, the combustion chamber structures, and keep in mind that number of fuel ports depends on the thrust level and shift in oxidizer fuel ratio during burn. As I told you that oxidizer fuel ratio will be changing along the length and along with the time as well, and it depends on the number of fuel ports depends on the motor length and diameter, and this also depend on the desired oxidizer mass velocity or the mass flux, such that you can have a higher thrust level. So, therefore, one has to be careful about this, and let us look at how does this volumetric efficiency vary, and also along with the L by D of the mass of the fuel, because volumetric efficiency is very important parameter to judge the efficacy of the fuel grain, and the volumetric efficiency is defined as the ratio of the volume of solid fuel to that of the volume of the grain at a particular instant of time when it is there. So, volumetric efficiency is influenced by the number of ports, wave thickness, and oxidizer mass flux. So, let us compare this data of volumetric efficiency, which is plotted in along with this, and the mass fuel of is in kg is plotted along with the horizontal axis. And you can see that 2 cases we have considered. One is single cylindrical fuel grain, and you can look at this volumetric efficiency very high when this mass of the fuel is very low. It is something around touching around maybe something 77 percentage, but unfortunately it goes on decreasing with the mass of the fuel increases. And keep in mind, for that one has to increase the L by D ratios. It is changing from 10.2 to the 26 when you are using 2800 kg of fuel. So, there is a large change in the L by D ratio. However, there is also large change in volumetric efficiency from 76 to the around maybe 42 kind of or 43 percentage. But whereas the 7 cylinder clusters, you can see that it is of course having a little lower value as compared to single cylinder, particularly for the lower mass, but it is changing, it is lowering down, but with a very minimally as compared to the single cylinder fuel grain. So, if we will summarize that a single cylinder port has a higher volumetric efficiency than that of the 7 cylinder cluster port for fuel mass flow below the 700 kg. If you look at this is the crossing point kind of things. But if you want to go for a larger mass of the fuel, that means the longer duration and also the higher thrust, then naturally one go for the 7 cylinder cluster design. And keep in mind that volumetric efficiency must be greater than 50% for a reasonable design, and which this 7 cylinder cluster design is satisfying, because it is all the time it is more than that. So, therefore, 7 cylinder cluster design is being preferred. Let us consider an example to illustrate how we can utilize the burning rate relationship for hybrid propellant for designing a hybrid propellant rocket engine. A hybrid propellant rocket engine is to be designed and to produce thrust of 1.5 meganewton, characteristics velocity of 1745 meter per second and thrust coefficient of 1.7 using STPB fuel and liquid oxidizer with oxygen fuel ratio of 6 with chamber pressure of 5 megapascal and temperature of 3000 Kelvin. The fuel grain diameter is 0.25 meter with fuel grain length of 3 meter. Determine the diameter of single circular fuel port grain to meet the thrust requirement for blowing ratio of 15. And we can take combustion gas viscosity as 2.1 into 10 power to minus 5 Pascal second. This is a basically circular cylindrical port, and we know that fuel grain diameter is basically given as 0.25 meter, and this is your fuel grain. And we need to find out basically this circular port diameter. This is the D, and it is already given this diameter, that is given as D, capital D this is. And let us look at what are the things are given. This given are basically thrust F is 1.5 meganewton, the characteristics velocity 1745 meter per second, thrust coefficient 1.7 and oxidizer fuel ratio is 6 and chamber pressure, that is 5 megapascal, and temperature is 3000 Kelvin. And the grain diameter, that is 0.25 meter, and length is given as 3 meter, and viscosity is given as 2.1 into 10 power to minus 5 Pascal second, and blowing ratio, that is B, is equal to 5. We will have to basically to find out is D, that is the diameter of the cylindrical port. And let us look at how we can find out. First of all, we will have to find out basically the mass flow rate of the propellant. That can be done provided we know the throat area. So, for that let us find out basically the throat area, and throat area we can estimate as is equal to F divided by Cf into Pc, and F is given, that is 1.5 10 power to 6 Newton, and Cf is 1.7 into 5 into 10 power to 6. So, this is cancel it out and you will get basically 0.1764 meter square. And we are interested to find out mass flow rate of propellant, mass flow rate of propellant, that is equal to m dot total, that is P is equal to Pc At divided by C star, and Pc we know and At also we know, that is 5 into 10 power to 6, that is your Pc, and At already we have found out 64 divided by C star. C star is basically 1745 meter per second, and that happens to be 505.4 kg per second. And we know that is oxidizer and fuel ratio, mass flow rate of oxidizer, mass flow rate of fuel is equal to 6. That is equation 2, but we know that M p is equal to m dot O x plus m dot f equal to 505.4 kg per second. This is equation 1, and by solving this equation, by solving equation 1 and 2, we can get m dot f is 72.2 kg per second, and m dot oxidizer is basically 433.2 kg per second. And in order to get this diameter, we need to also find out basically the mass flux rate, because we will be using empirical relationship, the semi empirical. For rho r dot is equal to rho r dot 0.038. You can say this is basically G. This is inner diameter of the port into 0.8, that is x by mu minus 0.2 into B 0.23. So, for that we need to find out G. So, if you look at G, basically we can find out as G is nothing but your, that is your mass flux rate is nothing but your m dot p by A p, that is 505.4 divided by A p, this is pi r I square, and this is your r I, 2 r I, this is basically you can say. So, therefore, you can get this is 160.9 by r I square, this is your equation 3 and this is your equation 4. And when you substitute these things here, we can get basically by using equation 3 and 4, we can have rho, this is your F, rho F r dot is equal to 0.038, G is already we have expressed in terms of Ri. So, I can get 160.9 Ri square, and this Ri square power to 0.8, and x is equal to 3 meter. So, therefore, we will take 3 divided by 2 into 10 power to minus 5 minus 0.2, 15 power to 0.23. So, that we can get is 0.384 divided by R I 1.6. Let us say that this is your equation 5. We know that mass flow rate, that is m dot f, is nothing but your 2 pi R I L. This is your total area into rho f r dot, and if I can put this here, that is m dot f we already know, that is your 72.2 is equal to 2 pi r I into 3 into 0.384 divided by R I power to the 1.6. So, this is your equation 6. So, by solving equation 5 and 6, we can get that R I is equal to 21.5 millimeter. So, therefore, the D will be 43 mm. So, we can find out this is your port area. So, here we have learned how we can utilize the semi empirical relationship for designing the port area in case of a hybrid rocket propellant engine. And with this we will stop over here. Thank you very much.